Before I start, I think I'd just acknowledge my co-authors. As you see, there's also Batista, Blanc, Berg, who just spoke and provided us with the data, Craig Ulrich, Patrick McClure, Haruko Wainwright, Ken Williams, and Susan Hubbard. And I would also like to thank Brad Carr, who did all the well logging for us, and also Lee Liberty and James Sinclair, who went to the field with us last October and also acquired actually a lot of seismic data, which I'm not going to show. So what are we trying to do here? So basically my aim is to take the data from Berg, so all the airborne resistivity data that we have, and try to link this to geomorphological indices and also vegetation types to basically do something that geomorphologists like to do. So just use these different kind of measures of your topography and try to estimate what the bedrock looks like. And why are we interested in that? It's mainly because we are in this mountainous watersheds where basically whatever goes into your river is controlled by processes happening in these hill slopes. And they can be alpine, where we have a lot of snowmelt going into basically the subsurface, or they can be montane, where we have rainfall. But no matter what source of precipitation you have, everything will go through the soil, the regolith, into the bedrock, and at some point will end up in your river. So clearly, whatever happens in these hill slopes is defining how much water, nutrients, carbon, but also metals are retained and released through kind of this process. And this process has kind of two timescales. First of all, it's kind of triggered by things like snowmelt, which is pretty sharp in time, or monsoonal rainfall in the summer. But it also has it's changing over decades, especially with ongoing climate change. So what we really want to do here is we are trying to understand what the bedrock characteristics are, because then we can actually determine what the flow properties are and kind of what are the redox conditions, so what is the biogeochemical conditions in the subsurface. So that's just as background. As Berg already said, we're in the East River Watershed, which is the study site of the SFA watershed function. It's an area of about 300 square kilometers with an average elevation of more than 3,200 meters and a topographic relief of more than 1,400 meters. So from these numbers, you can already see that we have to have pronounced gradients in hydrology, but also geomorphology, but also most importantly in terms of life zones. So we're going from alpine, which is probably more snow dominated, to montane environments. And the East River is feeding to the Gunnison River, which in turn goes into the Colorado River. So whatever happens in this mountainous watershed has an impact downstream on kind of water quality and water availability. Just a few pictures here, taken last year in October. We see here the meandering East River going through its valley. Here another picture of the East River. And while we were doing our survey, we also got feet of snow. So it's usually quite nice to go there. So what is our approach in terms of how are we trying to characterize the bedrock? So we're doing something very similar to what Berg just talked about. So we have data of different kind of resolution. We have drilling data, which of course gives you some point scale, estimation of rock properties, where we have full core recovery, so we have direct observation of the rock properties, but we can also take them into the lab and sample them. Then thanks to Brad Carr, we also have well logs, which give us mostly indirect measurements of a range of rock properties. We're trying to link this to the near-surface geophysics, which provides us with high-resolution subsurface images of resistivity and seismics. And then we're trying to use whatever relationship we get out of these to basically upscale these relationships through remote sensing and geological maps, where in particular geological maps gives us the geology, including its dip and strike. But we also have LiDAR data, where we get topography data, but also slope and aspect, which then helps us to feed these kind of geomorphological models. What's not shown here is we also have neon data, which is kind of hyperspectral data, which helps us to identify which types of vegetation we have. And then we have airborne electromagnetic data. So before I start, I think it's good to kind of define the hypothesis we are working on. Basically, what we want to do, or what we hope is possible, is that we can use the ground-based geophysical data, and together with these drilling results, actually come up with kind of some petrophysical models that we can use to then estimate bedrock properties based on the airborne data. And The property we are using is effective porosity, which we hope act as a proxy for fracture density and bedrock weathering. Take-home messages before I start. What we will see in the next few slides is that although the East River Basin, so I'm only going to talk about the East River bit, is mapped nearly entirely to be sitting on Mancos Shale, this Mancos Shale is varying tremendously throughout the watershed, which of course then has impacts on kind of release and storage of metal, carbon, and nitrogen. And what we also see is that the geophysical data surprisingly well correlates with LiDAR vegetation data, which then gives us another way of upscaling results. That's something you just saw from Berg. So again, that's the airborne EM data, just the very, very shallow surface layer, basically, so 0 to 5 meters. So I'm focusing just on this bit of the survey, so just the East River watershed. In addition to this, we have 3, let's call them intensive sites, where we have near-surface geophysical data, namely ERT and seismics, that usually spans from one side of the valley to the other. In addition to that, we also have boreholes, 3 that were drilled last year in October, all of them between 30 and 60 meters deep, with full core recovery in the shale unit, and 2 of them, the one up here in the north and this in the center here, were logged. So we have a whole suite of geophysical logging data. And unfortunately, this borehole was only cored because the material was so weak that we couldn't actually keep it open long enough to do the logging. So let's go to geophysics, ground-based geophysics. In the next few slides, we will see kind of the same arrangement. So on the top, we will see the slope that's just basically calculated from the LiDAR image. We have the geological cross-section at the site, just taken from the geological map. Then in the center is ground-based ERT. And then on the last panel is either seismic data or, in that case, the airborne electromagnetic data. And then on this side, we usually see a picture from the core that was drilled. So here the core is at basically 19 to 20 meters. All of this is basically what was recovered between nearly 17 and 19 meters. So there was hardly anything that was recovered. But if we look at the data, we can see here's the borehole, and we have this quaternary unit here that comes out as a very nice conductor, actually, sitting on top of this more resistive Mancos Shale unit. And you can see this here. So this is 10 meters, 20 meters. At 20 meters, we have this interface, both in the ground-based ERT data, but also you can see here the airborne EM model that's on a line that's actually perpendicular to this line, so there's only one section. But also in there, you can see the 20 meters pretty nicely. And once we reach 20 meters, we get some really nice competent shale. If we look at the inline data, so I shaded this out a little bit because in this bit here, we actually have, I probably guess, some IP effects. So actually the recovered resistivity section doesn't really agree with the ERT data, but neither does the inline and crossline agree, as you can see from this kind of cross-section here. So there are clearly a few issues there. Let's go a little bit further down south. So what I just showed you was the northernmost. So this is the site at the center. Here we crossed the East River. We didn't really manage to go up the other side because there's a small little village that starts there. But basically here what we have is we are mainly in the Mancos Shale unit with some shallow quaternary deposits on top, 5 to 6 meters thick. And again, we can see here that, okay, we have this quaternary layer that can be resistive, can be conductive. But underneath that, we have the Mancos Shale, which in this case is slightly less resistive than what we saw on the other on the previous slide. And this is probably because here it's a bit difficult to see, but the core that we recovered was completely shattered. So you basically had a whole sequence of very, very thin disks. But also in this disk, which could be stress-related, but also you had quite significant vertical fractures. And you can see this here. We have kind of high P-wave velocities, which kind of decrease a little bit, but we're also getting towards the end of the survey, so this has to be taken with a pinch of salt. If we go down then to the southernmost side, so now we're at the lowest elevation. So before these were both kind of subalpine environments, now we're in montane environments. Again, here the borehole. In general, we are just in Mancos Shale with thin quaternary cover, really, really thin actually. There's a bit of moraine deposit here, which comes out as kind of a more resistive unit. But in general, what you already can see is that the resistivity of the Mancos Shale is varying quite a bit. So here we have kind of, in comparison to the other side, still low resistivities. But if we go to the side where we actually drilled, there's kind of a conductive anomaly. And if we then look at the borehole core that was recovered at 40 meters depth, so down there, we see that there are a lot of fractures. So here, the effective porosity is really high because basically there's so much pore space in between these kind of competent blocks that there's a lot of water that could potentially be in there. We can see something similar in the seismic data where we have kind of comparably low velocities here. And if we look at the airborne data, we can see basically a similar trend. Here we get this kind of conductive layer overlying a resistive layer, and we get very similar results in the airborne data. So just very quickly, the two logs and just a subset of the data that Brad acquired. And probably most interestingly, this side is the one up furthest north, where we had this thick quaternary layer of about 19 meters sitting on top of this really nice shale. What we can see in the resistivity is that we have this really strong jump going from basically very low resistivities to very high resistivities. This correlates very nicely with porosity. So in the upper 15, 16 meters, we get very high porosities, up to about 50%, and then it goes down to about less than 10%. If we go to this intermediate side, we had very, very thin quaternary cover, so only like 5 to 6 meters, and below that we have a unit that's not really varying a lot, so you see the seismic velocities don't change a lot, the resistivity data doesn't change a lot, and also the porosity is pretty constant. What we then tried is we tried to relate the different geophysical properties to each other. So we see, for instance, that this quaternary fill that we had on top has very low resistivity, but also very low p-wave velocities. This side in the center where we had this really shattered shale, we have kind of slightly higher resistivities, but still kind of low p-wave velocities. And then once we get into the shale at the northernmost side, we get very high resistivities and also very high p-wave velocities. If we then plot the resistivity against the NMR-derived porosity, we kind of get this exponential relationship here, to which we can fit an Archie's law, which basically then gives us a means to translate our resistivities into porosity. And that's what I've done here, which is now showing the upper 20 meters of the airborne data. So you can see, first of all, that we have this kind of resistive units that Berg already pointed out, which are basically this intrusive rocks that we have here, and these also on this side. But in general, we have quite low resistivities in this East River Basin. So if we now use this Archie's law, basically as our transfer function, we can translate this into porosities, and we see basically a similar story, right? We have low porosities here, which, yeah, I mean, it's granite that probably has actually low porosity. If we go up to this upper side where we had this thick quaternary layer laying on top of the shale, we see that this also comes out as having a high porosity. When we then go back towards the lower side, we see that basically we have a gradient porosity where we have increasing porosity down here, but still some variability. And we see that at this site where we drilled, where we had this really, really fractured rock, we can get these really high porosities. And if we bring this back to resistivities again, as I pointed out before, it's basically the same story. So this brings me now to kind of our correlation of the subsurface resistivity with geomorphological and vegetation indices. And then why do we actually want to do this? I mean, as I pointed out at the beginning, there's quite a lot of work recently being done in geomorphology where people try to estimate soil thickness, but also regolith thickness just from topography alone. So mainly just from aspect and slope of hill slopes. So basically what we're trying to do is we're kind of trying to validate whether these approaches are actually working. And then we're also interested in kind of which type of vegetation grows on which type of bedrock or which type of resistivities. So what we see here is a violin plot where I grouped the data based on their slope aspect. So on this, we have northeast facing slopes. So if you remember, the East River Watershed is basically kind of a line like this. So you have either, or the majority of slopes is either northeast or southwest facing. So here we have northeast facing slopes, here we have southwest facing slopes. And then the different bars are basically the different slope angles. So blue is slope angles below 10 degrees, then we have 10 to 20, 20 to 30, and so on. And this small little dot here is above 50 degree slope. So we don't have much data, that's why it's so small. What we see in comparison now is actually that we get comparably smaller resistivities at northeast facing slopes, which means that we potentially have deeper weathering profiles and higher moisture content. And we get higher resistivities at the southwestern facing slopes, which means we have probably less moisture and less or shallower weathering. If you compare this to one of these geomorphological models by Pelletier et al., 2018, he basically tried to estimate this worldwide, right? So he came up with a model that holds for different situations. At Crescent Butte, we had a water-limited soil method case. And what he suggested is that for northeast-facing slopes, you have deeper bedrock weathering because you have more moisture and basically more vegetation. Whereas on southwest-facing slopes, you have thinner weathering horizons, and which basically because you have less moisture, because you have more radiation and hence more evapotranspiration. If you look at just the vegetation, we see that, well, probably what you would expect. So you get, you have smaller resistivities where you have meadows and shrublands, and forests generally tend to have higher resistivities. And if we split forests up into deciduous and evergreens, we can see that evergreens have even higher, or grow on bedrock with even higher resistivity than deciduous forests. So this is basically the last step that I've done now. So we have all this data, which seems to correlate somehow with our resistivities. So what we're trying to do now is we're trying to do the same as the geomorphologists. So we're trying to estimate resistivity based on elevation, slope, and aspect. But we used the vegetation map we have to basically create a linear mixed effects model, which means that for this linear relationship, we assume that the slope and the intercept can or varies with vegetation type. And what we get is this kind of reasonable agreement, which we see down here. So this is our measured data and our estimated data. And they kind of follow the 101 line. But of course, we get quite a bit of scattering around it. In this plot here in the back, we have the estimated resistivity, and then what you can see here, and sometimes these are the actual airborne EM flight lines for the upper 20 meters. And most of the time, actually, you don't really see them because they agree pretty well. In other areas, they don't agree that well. So clearly, we are kind of underestimating high resistivities, and we're overestimating sometimes low resistivities. And then we can use our Archie's law to estimate porosities from this. Just as kind of sort of trying to validate this approach, we see here now that I split up these, the East River watershed into 11 sub-basins and calculated the mean porosity for these sub-basins and compared it to data from Rosemary Carroll et al., which they published just last year, where they basically look at the fraction of groundwater, snowmelt water, and basically runoff in the streams, and just compare it to the groundwater fraction they found in these different sub-basins. And what we find is that sub-basins with like low groundwater fraction seem to show low porosity, whereas if we have sub-basins with high groundwater fraction, we tend to see also high porosity. The only outlier is number 9 here, which is this. This is Copper Creek, which also has quite a different geology compared to the other basins. But basically what this tells us is that if we have low porosity, we have low storage. So this brings me to conclusions. What we saw is that the bedrock characteristic, even though everything is mapped as geology, varies tremendously. So we have the same geology, but clearly different hydraulic properties. This means that we get different residence times, different recharge, discharge, and different nutrient release and storage. What we also saw is that the airborne data is actually in good agreement with geology and ground geophysics, but also with the geomorphology and the vegetation types. So this clearly then opens opportunities to upscale bedrock properties, as I've shown, which then builds a basis to kind of build predictive models of these kind of processes in the critical zone. And that's also what we're trying to do now. We're trying to bring this approach into hydrological models to basically get a better or improved predictive capabilities and better understanding of the processes that are going on in this watershed. With this, thank you very much.